time.
Hi everyone, I want to introduce our speaker, Alec Koppel. Alec did his undergrad and master's at WashU in mathematics and system sciences. And then he joined Penn as a PhD student, and he's a 4-year PhD student working with Arrow-Hurwicz. He's also a smart fellow, if I'm right. He's a smart fellow supported by Army Research Lab. And today he's going to talk about online learning and pattern recognition in multi-agent systems in a while. Okay.
Thanks, Ariane. So, yeah, the title of today's talk is Online Learning and Pattern Recognition in Multi-Agent Systems. And what I really mean by this is we're going to be talking about strategies for learning and adaptation in networks of interconnected agents. So, in particular, a multi-agent system is a blanket term for a network of interconnected agents with some common global objective. And this objective is comprised of the local objectives of each agent. And so this framework is hinting at the idea that each individual agent has, with access only to local information, is interested in learning something that is global to the network. And in order to do so, the individuals have to communicate with their peers, and their ability to do so is given by some underlying network structure. So this framework describes a number of engineering applications, such as sensor networks, groups of interconnected cloud computing systems or computer servers, and the messiest of these mobile robotic teams. And so, since a multi-agent system is a very generic term, it encompasses a number of different problems that have been studied in the past decades. And which problem setting you're in depends on the structure of these objectives as well as the communications network. So, in particular, these objectives that determine what goals the individuals on the network are interested in can either be deterministic functions, or they can be stochastic or online. And the structure of these functions motivates various distributed optimization algorithms. And as I said before, there are various settings for the communications network. This network can be fixed and known. It can be varying in time, or it can be unknown. And this has motivated work such as consensus methods or gossip algorithms from the communications literature, and also graph inference problems, respectively. So the focus today is going to be on the case where these local and global objectives are online, aka they depend on sequentially revealed information, and the network is fixed and known. So now I'm going to go into a little more detail about what I mean by online learning. So this doesn't have too much to do with the internet, but instead refers to the idea that information is sequentially revealed. So online learning is a formal framework for describing a family of adaptive algorithms, and it can be I think to understand what is online learning, we should first contrast it with what is offline learning. So offline learning refers to your classical model fitting strategy in statistics, where you're given some batch of data and you select your model parameters, such as regression coefficients, to minimize some residual error over this data all at once. So online learning inverts this procedure by considering the case that some learner is interested in repeatedly updating their, say, regression coefficients based on newly revealed data. And in this problem class, regret is the essential performance metric, which measures how well this learner is adapting to new information. And what regret measure is the the number of mistakes this learner makes as compared with some fixed optimal offline learner, which has access to all of the information in advance. To be more formal about this, we can think of this as a repeated game between between an agent and nature. So at time 0, this agent selects the model parameters x0, after which nature reveals its loss function, and the learner suffers some loss f0 of x0. Now, what the learner would like to do is make this loss at nature's loss at the next time small, but doesn't have access to it. Nonetheless, it selects its next model parameters, after which nature reveals its next loss function, and so on and so forth. And we get this repeated chain where at the tth time slot, the agent selects some model parameters xt, after which nature reveals this arbitrary, potentially antagonistic convex loss function ft, and the learner suffers the loss ft of xt.
There is only one agent, right?
Yeah, for now. And so, as I said before, regret is the essential performance metric for this framework, and what regret measures is the running time aggregation of the cost of nature's costs evaluated at these instantaneous losses, as compared with the the optimal offline learner, which is computed with all of nature's functions revealed in advance. So regret is measuring the price for causal operation, in the sense that it measures how much we pay for not being able to see into the future up to some finite time window, capital T. And so the goal of online learning is to make the time average regret go to 0 with increasing capital T. And one surprisingly simple strategy which achieves this is online gradient descent. And online gradient descent just involves having the learner select their next action to descend along the gradient of nature's function revealed at the previous time slot. So here we're just going to draw some connections between online learning and stochastic approximation, which will allow for a more seamless transition to some incorporation of pattern recognition techniques later. So in particular, in most practical settings, nature's function implicitly depends on realizations of some random pair theta and y. So here we can think of theta as feature vectors and y as some labels or some physical measurements. And if this random pair is, if these realizations are sampled uniformly from and independently from a joint distribution, then the time average of nature's functions and the limit as capital T goes to infinity may be written as an expectation over this random pair. So through this observation, we just note that time average regret going to 0 is equivalent to solving a certain kind of a stochastic optimization problem where this function f is convex. And so I guess now it's important to emphasize the difference between these two frameworks. So in stochastic approximation, what we're learning is an x star, which is learned over all possible data realizations, but we do introduce a distributional framework, as I noted here. Whereas in online learning, there's no distributional assumptions made, so nature's functions can be arbitrary or even antagonistic. So depending on the situation, one or the other may make more sense. So now we turn to extending the problem of online learning to multi-agent systems. And, so the way we do so is by defining a network in the usual way as a pair of a set of vertices and a set of edges. And here we assume that we have n nodes and m edges, and we define the neighborhood of a node I in the usual way. And so there are multiple ways we could extend the idea of online learning to networks. I think that the most straightforward would be to now associate with each node a local repeated chain where at each time it selects some model parameters, after which nature reveals some local loss. But this would effectively be n parallel local games. So we're actually we're not going to do that. We're going to instead consider the case where individual agents are interested in minimizing some global loss, which can be written as a sum of all of nature's local losses at each time, at each node. And each agent I wants to make this global loss small, but it only has access to a locally revealed cost. So therefore, in order to make this global loss small, it needs to collaborate with others and do some exchange of information. So to go under the hood here a little bit and illustrate what I mean, so if you note in the middle slice here is exactly the same as the cartoon we had of online learning before, but now before each selection of model parameters, agent I is now allowed to do some information exchange with its neighbors, which will be deliberately vague about what that is for now. We'll fill that in later. And then, so after agent I selects its model parameters, then nature reveals its local cost, and the learner suffers this local loss FIT of XIT. But the agent is actually interested in minimizing the global cost, which it doesn't have access to. So therein lies the motivation for this message passing. And just we note that we're still in a distribution-free framework, so nature's functions can be arbitrarily different at distinct nodes.
But you think maybe convexity is something there?
Yes. Yes. I think more or less difficult it's a vague question. It depends on how you're measuring difficulty. One thing I would say is it's apples and oranges. They're a little different from each other. But I guess in general I would say more difficult. So the central claim of this work is that learning in networks is possible in the sense that we can develop model selection strategies for individuals in the network to make a networked analog of regret small in some time average sense. So, in the past, people have approached this kind of problem with the consensus protocol, and what I mean by this is each agent would, incorporate some mixture of its local gradient and a weighted average of the model parameters selected by its neighbors. So we're going to do something a little bit different. We're instead going to develop a primal dual method, which operates by tracking the price of disagreement of how much tracking the price of disagreement of different agents' model parameters. And so what we're able to show is that we can still achieve a regret bound that is comparable to the centralized case. So as I said before, there are a number of ways we can extend the idea of online learning to networked settings, and so one and when when we do so, we also need to think a little bit about how we generalize the idea of regret. So in particular, the most straightforward thing we could do would be to substitute nature's global cost function into the definition of regret we had in the, I think, third slide. But if we do this, then this refers to a problem in which individuals are all required to select a common decision variable, and this actually wouldn't be that interesting. We're instead going to consider the case where individuals are allowed to select model parameters which are not necessarily the same. And so, if we allow for this modification, then we obtain uncoordinated regret. And again, so here we can note that uncoordinated regret actually decouples along each node. So individuals can control the growth of this quantity by essentially just operating in a local echo chamber. So we're actually not that interested in this case either. We want to formulate a problem in which individuals are allowed to operate autonomously, yet they are incentivized to collaborate. And the way we do that is by considering a definition of regret in which the decisions made by node I are coupled to the costs revealed at all other nodes j. So in particular, we define the local regret of node I as the evaluation of node I's actions at the costs revealed at all other nodes. And the running time aggregation of this quantity as compared with the global batch learner, which is optimally computed with all of nature's functions revealed in advance over the entire network. This is how we define local regret. And by further considering a node average of all local regrets, we define global network regret. And so these are making these quantities small in a time average sense is what we mean by learning online in a networked setting. So this is measuring how well individuals learn global information when it is sequentially received locally. So now we turn to actually deriving an algorithm to ensure the growth of local and global networked regrets are small. And the one way in which we could do that is just by introducing an agreement constraint. And so in particular, at each time t, we would like to require node i's actions to be equal to all of its neighbors. And by stacking up all of individuals' decision variables into some very large vector xt and using the node edge incidence matrix, we can compactly write this as cxt. But note that enforcing this constraint exactly at each time would require global coordination. So rather than enforcing this constraint, we consider the Lagrangean relaxation. And so we define the Lagrangean relaxation of the networked learning problem as the global cost associated with nature's functions revealed at each node, plus this constraint slack term. And here, this Lagrange multiplier lambda t is measuring the price for disagreement. So,
what is the motivation in enforcing xit to be equal to xjt? So the neighbors all have the same actions, is that?
Right. So I guess in the definition of coordinated regret, all agents are required to play a common decision variable. So in the modification or generalization to the definition of networked regrets, we note that still we are tying individual nodes' actions to the costs of all others. So in order to make those costs, so in order for node I to make the cost revealed at node j small, it needs to not be too far from the value that node j is selecting. Does that make sense?
Yep. So you are considering non-cooperative game or cooperative game?
It's cooperative here. But I think one of the most interesting remarks about this work is that this is actually not the Lagrangian of any optimization problem, or it is the Lagrangian of some optimization problem, but we haven't discussed any thus far. But nonetheless, it's a key analytical tool for making global networked regret small. And this is a convex function in the stacked decision variables and a concave function of its Lagrange multipliers. So now we actually turn to deriving an algorithm to make global networked regret small. And the way in which we do so is by applying the saddle point method of Arrow-Hurwicz. And this saddle point method operates by alternating primal descent and dual ascent steps on the online Lagrangian. And so, in particular, as I said, this allows us to derive a distributed algorithm where at each time node I does essentially online gradient descent plus some dual correction term which incorporates the Lagrange these Lagrange multipliers. And what these really do is allow it to observe how much its decision variable disagrees with that of its neighbor. So, if we go up to our cartoon that we had before, now agent I before selecting its current action does some exchange of Lagrange multipliers with its neighbor, and its neighbor returns in kind, and then it uses this information to perform this dual corrected online gradient descent step. And then along the communication links of the network, we update the price of disagreement of node I and j based on how much they disagree. So now we turn to discussing some analytical properties of the saddle point method for the networked online learning problem. In particular, if we run the saddle point method on the networked online learning problem, then the uncoordinated regret plus this constraint slack term are bounded on the order of square root of t. As we noted before, the uncoordinated regret is actually not the objective of interest, but the presence of this constraint slack term allows us to relate uncoordinated regret and networked regrets through the Lagrange multiplier here. And so here we have our main result, which just says that the saddle point method achieves a square root of t regret bound in terms of the networked regret. And if we run the algorithm with constant step size, 1 over square root of t, and here the learning constant depends on initialization, network data, and smoothness properties of the loss function. And so what this is really saying is that the saddle point method achieves a networked regret bound that's comparable to that of online gradient descent. And here we have another theorem that says that individual nodes learn at the same rate as the network in aggregate. So here this is local regret rather than the global version. So now we're going to discuss some of the examples I introduced at the outset. So in particular, we just consider
Before you move on, can you also mention what are the other terms which affect the constant that that we're finding in the O, what does the recursive handle?
So this M is the number of edges. This C lambda is dependent on the way in which we define an optimal online dual variable. And these Lx and L lambda are the primal and dual gradients of the online Lagrangian. They're bounds on those gradients. No. The Lipschitz constant is subsumed into actually this definition of the Lagrange multiplier set.
So if your degree of the node is higher, then it is bounded higher.
Or the learning constant is larger, but the rate is the same. So yes, in very large networks, you see learning happening at about the same rate, but it starts from a much higher place. And so now we're just going to turn to a simple estimation, sequential estimation problem in a sensor network. In particular, if we consider the problem where each sensor in the network is receiving observations, which are a noisy linear transformation of the signal it's actually trying to estimate. In this context, with some noise perturbation, we see that the time average local and global regrets are going to zero at approximately the rate guaranteed by theorem 1 and 2. And moreover, if we measure the deviation from consensus of the network in an average sense, aka the Euclidean distance of the average vectors of individual model parameters relative to the magnitude of the globally optimal estimator, we see that this quantity is also going to zero. So we see consensus is achieved. So now we turn to a slightly more interesting example of a multi-agent system. In particular, we consider the case where each node now represents some server. So say we have some group of interconnected servers like that of Penn and Princeton and Columbia and et cetera. And these servers are interested in maintaining some minimum quality of a service guarantee, which in order to provide that, they need to prevent malicious users from connecting to their network. So the way in which they do this is by tracking the information of users connecting to their network, building feature vectors based upon this information, and the information they track is like, buffering data and a number of failed logins and protocol types and user bit rates, et cetera. And then based on these feature vectors, they try to predict some binary label that denotes whether a user is going to be an attacker or not. And so we consider the case where each node wants to train online a support vector machine classifier. And we note that user information could vary wildly from one server to another. So if Princeton's users are much more useful for detecting a certain type of attacker than Penn's, then if Penn would like to learn to defend against that type of attacker, they have some incentive to collaborate or exchange information. But they might not want to exchange user information directly due to some privacy concerns, et cetera. So fortunately, the saddle point method in this context allows for a protocol in which the different nodes, by only exchanging their classifiers and their Lagrange multipliers, are able to pool their information. So in particular, for a practical setting with the knowledge database and discovery data, data set regarding detecting attackers in computer networks. We run the saddle point method for a support vector machine classification problem on a 50-node cycle network. And here we see that the time average local regret is going to 0 at approximately 1 over square root of t. However, since the hinge loss associated with support vector machines is non-differentiable, we see these large spikes whenever a mistake occurs. But nonetheless, the algorithm quickly recovers. And again, I should emphasize that no direct exchange of feature vectors is necessary for this kind of learning. But more important performance metrics for how we're actually able to learn are the number of friendly users that are denied service, which we call the false alarm rate, and we note that this settles around 30%. And then we also consider the error rate, which is the number of attackers that the algorithm failed to detect, and this settles in the close to 90% accuracy. So I think the first two examples of multi-agent systems were fairly clean, but one example of a multi-agent system which is of increasing importance these days is robotic networks. So these. In particular, people are interested in autonomous robots mostly for first responder applications. So they want their robot to, perform information aggregation or inferences in situations that are hazardous to humans. And in this situation, why use more than one robot? I think the main argument is, redundancy. So if the robot is operating in a hazardous situation, it could easily fail. So if there are more robots, then we are more likely to be able to actually learn and learn what we're trying to discover in the environment. And in this situation, so clearly there's an argument for teams of robots in first responder situations, but mostly these days, the information processing techniques that are on these that are deployed on these multi-robot systems are based on centralized information processing. And for the most part, these work well. But for certain cases, say the individuals are trying to learn about some signal that's non-stationary or varying somewhat rapidly, then the time delay associated with centralization might not be able to be afforded. So this motivates the use of distributed algorithms in robotic networks. So I guess I need to note that in robotic teams, there's a number of important unsolved problems. One surprisingly simple one is just autonomous navigation in unknown environments. And so what we would like to do is, through some distributed information processing techniques, allow for more effective autonomous navigation in unknown environments. And so here's the cartoon we have in our mind. There's some robot that's driving along some particular path, and this path may have that it's traversed may have omitted crucial regions of the feature space for its ability to effectively navigate. So by exchanging information with others, it's actually able to navigate more effectively. But we have to note that empirical robotic data is very messy, so more sophisticated information processing techniques are required than what we've discussed so far. So in particular, here's where we're going to make use of that connection between online learning and stochastic approximation. We noted that in the centralized setting, these sequentially revealed functions by nature are implicitly dependent on a realization of some pair of random variables where this y could denote some set of labels or some physical measurements, and theta is feature vectors. And if the relationship between this random pair is complicated, then it may be potentially advantageous to use an alternative encoding of the feature vector theta. So then the question becomes how to select a good signal representation, and so this gets us into the territory of pattern recognition. So pattern recognition is mostly about finding latent structure in data, and most methods rely on finding alternative signal representations of your feature vectors. So the classical techniques people use are Fourier basis or wavelets or principal components, which is based on some eigendecomposition. In contrast to those methods, in dictionary learning, we seek to learn a signal representation directly from data. So we're going to introduce this idea of dictionary learning and then discuss how to actually select signal representations that are tailored to a learning task we're actually trying to solve, and then we're going to discuss how to implement this in a multi-agent setting. And the reason we're trying to do this is because we would like to improve the performance of visual navigation of robotic teams. So now we get into some more specifics of the idea of dictionary learning. In particular, we're interested in representing some feature vector theta as a combination of some k common basis elements, which we stack into a matrix, which we call the dictionary, and we denote the coding of the feature vector as alpha, and that we introduce a representation loss, which is small if the product d alpha t and theta t are close. So here this product d alpha is the representation of the signal theta with respect to the dictionary d. So the coding problem is to select coefficients which make this representation loss small. And the dictionary learning problem is to minimize the representation loss with respect to the dictionary as well. As we note that that this coding implicitly does depend on the dictionary over which the signal is represented. So now we're going to extend this idea of dictionary learning to the task-driven case, which is where we want to learn some signal representation that's well suited to the actual learning problem we want to solve. And the way we do this is we first start out with the classical expected risk minimization problem that you see in machine learning, but rather than using feature vectors, we substitute the coding of that feature vector n. So the idea here is we have some decision variable x, which represents the prediction or model parameters, and y is our label. And what we would like to do is predict the label y given this optimal coding, so we substitute this optimal coding into your standard convex loss function that you see in many machine learning problems. And so the discriminative dictionary learning problem is the joint minimization of a dictionary and model parameters with respect to this representation loss, or this loss function, predictive loss function. And so this is a non-convex stochastic optimization problem. So in general, we can only find a local minima of this kind of problem, but in practice, these tend to perform pretty well. So here we just have some details about how to extend this to multi-agent settings. So in particular, we introduce agreement constraints, and then we relax them, and we consider the stochastic approximation of this of the Lagrangian of this optimization problem, which has the agreement constraints. I'm gonna go pretty quickly through this because it's very similar to the way in which we formulated the networked online learning problem with the online Lagrangian. The key difference here is that now we also have a constraint for this dictionary, and so then we also have an associated Lagrange multiplier. And so here this function, we're writing the dependence on the random pair explicitly, but just implicit in this expression is the representation of this feature vector with respect to the coding. And then we consider again the saddle point method of Arrow-Hurwicz which just amounts to alternating primal descent and dual ascent steps on the stochastic approximation of the Lagrangian of this problem. So note that this step and this step are essentially the same as the method we saw before, but now we additionally have updates for these dictionaries and these Lagrange multipliers, which penalize the disagreement of how much one agent's dictionary varies from another. And here are just some details for interested parties, but I'll just note that this method does yield a decentralized information processing technique for this problem. And here we just have a theorem that asymptotically the saddle point method converges in expectation to a stationary point of the problem, which is one of the stronger results one can hope to achieve for general non-convex problems. And so now we're just going to discuss briefly some image processing experiments which help us gain some design principles for actual deployment of this method on a robotic team. So in particular, we now imagine that each agent is actually here. It's a robot, but it's just some node, and it receives some images which it partitions into little patches, and it wants to classify these image patches. And the reason for this is, if a robot can identify the environment in which it's operating, and that certain things are buildings and certain things are grass, then it can use this information to modify its navigation techniques that are on board. So for a simple for a toy image processing experiment, we just compare how much do individuals suffer or gain when they observe information from all regions of the feature space, as compared with the case where they're observing distinct subsets of the feature space. So here the blue line is showing the learning performance of an individual node in the network, which is observing images that are coming from all label classes. So here we have like a multi-class logistic regression problem with like 5 classes. And here the green line is showing the case where each individual agent in the network is observing only random subsets of the total number of classes. So what we're able to see is that the learning performance is comparable, and we also see this in the sense of classification accuracy. But now we turn to actually discussing how this performs in a field setting. So here we've actually actually deployed a network of 3 Husky robots to drive around this robotics test facility in North Carolina, and these robots, they have some onboard camera, and they partition their images up into little patches, and then they attempt to classify them in order to use this information to modify their onboard navigation. So the textures, I probably don't need to say this, but they include building and sky and ground and a few others. And then when we actually see how this performs in practice, we see, as I noted before, empirical robotic data is a more difficult setting than the toy image processing database, but still we see reasonably good performance. And I guess with that, I would like to conclude. And here are just some references. Take questions. Okay.
In the last experiment with the Arrow-Hurwicz, did you look at, were they always within connection with each other? Could they always communicate to each other?
Yeah. So as I said,
and go far away.
Right.
In this case, when you have only 3 agents, it's easy to do
it's easy to do pooling. Yeah. I agree.
So I think it would be interesting to look at what happens if, over time, the communication among them changes. Right.
I think so. As I had said, I think at the beginning here we're considering fixed known networks, but yes, I agree. It would be very interesting to see how this performs on a switching network where the switching probabilities is dependent on some distance model of where these robots are in their environment. I think that would be a very nice experiment to perform. Analytically, it would be very challenging. Sorry, question.
Wait, sorry. So you said that all your graphs are connected.
They're right.
Could you please bring the update for the Lagrange multipliers based on meters?
This or way back? Here or here?
Just here because the loss functions, they don't have externality. It's not clear to me if it does a gradient descent privately based only on its own function and its own previous choice. Wouldn't they still achieve sublinear regret? Because these functions are still function on one variable. You're not working with functions that have externality.
So that's a good question. It would achieve sublinear uncoordinated regrets. But if you look at the way we define the networked regrets, node i's decision is coupled to the cost revealed at node j. So operating in the proverbial echo chamber would not suffice to make this quantity small. No.
Okay, so you're sure for, because it's not immediately different, that if you have two things. Because they are being drawn from the same class at each step.
No, they're not actually. They could be arbitrarily different. They just have to be convex.
So the union is not can we imagine that they're being drawn from the union of all these n classes?
Yes.
So if you consider that union, it's even a simpler version. But if you do a gradient and product gradient with respect to the union of those classes, you still get something everywhere. You are even communicating with each other.
So you're saying, okay, if I know in advance that the losses revealed at each node are partitioned into some number of classes, then individuals within one class should operate as a unit. Individuals within another class should operate as a unit, or
Just in it, I'm not sure, but maybe if the agent ignores the data from its neighbor and does gradient descent based on its own some functions delivered to itself, you would still get some linear global recurrence.
no, I don't think so. I don't think that would.
And if the functions that were depending on the choice of all the neighbors, for example, if you have fi depending on xjj in the neighborhood of I, then it would be obviously you cannot just linear recur just based on your own choice. But as long as the functions don't have externality, it's not clear why you need to communicate with other neighbors to get even global sublinear.
Right. So I guess if you're saying if this j was just a sum over i's neighbors, it wouldn't need to communicate? Is that it?
Instead of a sum over fj, you have a function that is dependent on, it's a convex function, but it's a multi-coordinate, multi-argument convex function. Then it's obviously that you cannot get sublinear recurrence without complicating.
Right.
But then when you're writing it as a sum of fj's, it's not clear to me why you just based on your own fi you cannot get, because all these fi's are coming from a common.
No, they're not coming from a common. So you can think of regret I as node i's objective. So it's intrinsically coupled to.
Maybe a suggestion, Alec. I mean, you gave the correct answer when you asked the question for the first time, which was that you didn't explain it properly. So
Oh.
if you go back to your first answer and explain it.
I think we should. I mean, I think maybe this is a discussion for the whiteboard at a later time, maybe.
So yeah, a further question about this enforcement, like xi equals xj, or in dictionary learning, they will have the same dictionary.
Yeah.
So I guess the assumption is that the network is all connected. And
Yes.
at optimal, all their dictionary, all their variables
Should be
the same.
coincide.
But this may not be the case for every time point. So you add this Lagrangean,
Right. Exactly.
and like you.
That's how we, try to incentivize this constraint.
And the interpretation for dual variables is the difference.
Right.
In
Or like the price of disagreement.
the price of disagreement.
Or it's like a disagreement penalty.
Okay, so for dictionary learning, what's the interpretation of the dual variable corresponding to?
To the dictionary. So node I is trying to learn some dictionary that's tailored to the learning task it's interested in, and that might not necessarily be the same as other nodes if they're not observing the same observations. But if you suppose that they're actually trying to solve the same global learning task, these Lagrange multipliers, I guess, track how much these dictionaries disagree. But there's a less clean interpretation of the way the dual variable operates for the dictionary.
Yeah, so
I
if the
think.
classification problem, let's say for dictionary learning, is different for different nodes, then they may have different dictionaries.
Right.
This may not be a
The-
difference.
Right. So I think, it's a good point if one robot is driving through the forest and another one's going through an urban environment, then maybe having them learn similar dictionaries wouldn't be the right thing to do. So, but I think that's like a little more in the future work domain.
But in that case, those two robots may not be connected.
Right. Yeah. So.
I was just wondering, so what class are those functions restricted to? Because on like the first line of that slide, it says unique global optimal whatever outline strategy. So that to me implies strong convexity as opposed to sort of arbitrary.
Right. So I guess I was sweeping that under the rug a little bit. So here we're only assuming convexity, but so it's not an absolutely unique optimum. It's like a set of unique optima. Right.
And then later on, you get a non-differentiable problem. Like
But
image loss, and then
right. But that's still convex.
I thought it's convex, but Alec, what's the gradient of non-differentiable?
It is, it's a maximum, no, there's an indicator that appears for the gradient of the hinge loss, subgradient of the hinge loss.
Yeah, I was going to say it should be a subgradient.
Yeah. Yeah, here you can, it all works out if you interpret gradients as subgradients, which in support vector machine you have to do. But I think we're out of time as far as questions go. So thanks for all the feedback. Did I screw this in? Let me turn this.